Hello and welcome to our presentation. We are Team Context Bandits and today we are presenting the paper Your TTS towards Zero Shot Multi-Speaker TTS and Zero Shot Voice Conversion for Everyone. This paper was published as part of the effort to improve speech synthesis systems, especially for new unseen speakers and low resource languages. Over the next few slides, we'll walk you through what TTS is, what the challenges are, and how Your TTS proposes a unique solution. First, let's quickly understand what TTS or text to speech actually is. A TTS system takes in written text and produces human like speech. We see it in action every day in Google Assistant, Alexa, and even in accessibility tools like screen readers. But while it sounds simple, building a good TTS system is hard. Why? Because human speech varies across speakers, accents, and languages. Most models work well only for a single speaker or language. Once you try to use them on a new voice or a different language, they break or lose quality.
We all interact with text to speech every day through assistants like Alexa and Google. But have you ever noticed they usually just have one default voice? That's because creating natural sounding speech for many different speakers is incredibly difficult. Our goal is to break past this one voice limitation. We want to create a TTS model that can clone any voice, even one it has never heard before, from just a few seconds of audio. We want this to work across multiple languages, even those with very little data available. This is what we call zero shot multilingual TTS.
The goal of modern TTS models is to do three things. First, clone voices the model has never heard before. This is called zero shot voice cloning. Second, speak in multiple languages using the same voice. And third, work well even with very little training data. These are the key challenges in building powerful and flexible TTS systems today.
Now we aren't the first to tackle this. Previous models have made great progress. For example, Tecotron 2 used speaker embedding to create different voices. Attentron used attention mechanism to focus on vocal style, and SC Glow TTS introduced a flow-based model for efficient zero-shot synthesis. However, they all share common limitations, like they require huge amount of data and large number of speakers for training, which makes them impractical for low resource languages. They don't support multi-language in a single model, and there's often a noticeable drop in quality for speakers the model wasn't trained on. This brings us to our solution, Your TTS. Your TTS is designed to overcome these exact challenges. Its key contributions are what make it a significant step forward. First, it achieves true zero-shot multi-speaker synthesis. You can give it a few seconds of anyone's voice and it can generate speech in that voice. Secondly, it's truly multilingual. It can learn from and generate speech in multiple languages within a single model, maintaining the speaker's vocal identity even when switching languages. And finally, it excels in low resource scenario. Your TTS can be trained on new language with just a single speaker, making high quality TTS accessible for languages that were previously left behind. It's the first open source model to successfully combine all these three of these critical features.
I'll take you to the model architecture as to how the model uh, is is trained basically to understand to better understand the input text and for using both the input text and the audio. So and as input we have a linear spectrogram, which is basically the audio waveform converted into the radar spectrum. We have an input text, we have a language ID, which is basically just correlating to the input text, which is converted to the audio, and the language ID is just to capture whatever the different languages. This is mainly done for multilingual synthesis. We also have as input a reference wave of any speaker, so just a small, it's a very short duration, audio of very short duration, which is basically being used in global conditioning of the model to better understand the speaker characteristics. Next to the process, the input text as compared with the language embedding, this means that the entire vector is created, and then it is also transformer-based encoder, and then it is being projected to basically as an input to the monotonic alignment search. I'll get to what the monotonic alignment search is in a bit. At the same time, the linear spectrogram is passed through a posterior encoder, which basically maps it to a latent variable Z. And Z is basically an internal correlation between the audio and the linear spectrogram. Basically, how the audio should sound and compared to the linear spectrogram, which is then passed through a flow-based decoder, which basically gives us a prior ZP. So basically prior guess of how the audio should correlate to the text. So now at the monotonic alignment search, from one side we get the prior ZP, and from the one side we have NP. So it's basically we have an audio frame at one side and the text input at the other side. So the main aim of this monotonic alignment search would basically be to map the text words to the corresponding audio waveforms or something like that. So the text words of the first AI words are mapped to the first J frames, and the next set of words are then mapped to the next set of audio frames. And this is done using a dynamic programming kind of an approach, wherein we say that the probability that this particular tokens of text belong to this particular audio frames is maximized. That is how it works. And there's another part in there wherein we have the speaker reference wave, as I mentioned earlier, is passed to a speaker encoder. It's a pre-trained speaker encoder with a pre-trained speaker encoder which gives out a speaker embedding. So this is basically done to capture the identity of the speaker as to how he's varying his voice, how his pitch is changing, how his tone is changing, what his accent is. For different languages, it matters a lot. So that is where all these things are captured, and then these are used in global conditioning for the entire training pipeline.
So now the another important part is our stochastic duration predictor. So which learns the rhythm of the speech. Basically, how long each phoneme or character should last. So during the training, it learns from the real audio, but during the inference, we don't have the real audio. So what it do, it samples duration from a random noise through an inverse transformation, and this randomness helps to create more natural variations in rhythm. So just like our human speak. Okay. So once we have the correct latent variable z, it is passed into the hi-fi GAN vocoder, which used in the paper, which finally converts it into a waveform that we can listen to. The vocoder ensures that the speech sounds really in high quality and more realistic, like a human speak. And to make sure that the generated speech not only sounds robotic but also sounds natural, so it uses which is called a speaker consistency loss, which is loss used in the paper. We compare the speaker embeddings of the generated audio with the real audio which we provided as an input, and we push them closer together using the cosine similarity between them, and this teaches the model to preserve the voice characteristic of the target speaker. Now, to make the YourTTS model multilingual, the authors trained it on the different datasets on mainly three languages, which are English, Portuguese, and the French. So first they prepared the audio data. They sampled everything to the 16 kilohertz, removed a long period of silence, and it normalized the volume so the samples were consistent. For the English, they used the VCTK datasets, which is quite large, of around 109 speakers. In some experiments, they also added even more English speakers from the Libri speech dataset. For the French, they used the M AI Labs datasets, which added another 5 speakers to the training. Uh, and for the Portuguese, they intentionally used a dataset which is only a single speaker. So this was the test to see if the model could learn a new language from very limited data and still successfully clone new or unseen voices or not. Now let's look at how we evaluated our model. We used three key metrics: mean opinion score. Human listeners rate how natural the generated speech sounds on a scale of 1 to 10. Speaker similarity, or SIMMOS, again rated by humans, but this time they judge how close the generated voice is to the target speaker's voice. Speaker encoder cosine similarity, or SECS. This is an automatic metric
We pass both generated and target audio through a pre-trained speaker encoder and then measure the cosine similarity between their embeddings. Higher SECS means the generated audio is closer in voice characteristics to the real speaker. Now the results. On English zero shot text to speech with the VCTK dataset, your TTS achieved near human quality, MOS around 4.2 out of 5, and similarity scores very close to the ground truth. This actually outperforms previous state of the art zero shot TTS systems like SC Glow TTS. For Portuguese, where training data had only one male speaker, the model was still able to generate new speaker voices in zero shot mode. Female speakers were harder, but still achievable, which is impressive given the low resource setup. Finally, they showed that with less than 1 minute of audio for fine tuning, the system can adapt to a completely new voice and match near ground truth similarity.
In addition to that, your TTS also supports voice conversion and speaker adaptation. For zero shot voice conversion, it can change one speaker's voice to another with good quality, like a MOS of 4.2 for English. And for speaker adaptation, it learns a new voice using just 20 to 60 seconds of audio. After 1500 steps, the similarity improves by about one slim MOS point, which is a big jump.
So a few limitations to our YourTTS model is basically first we start with unstable durations, or let's say our timing comes from the STP or the stochastic duration predictor. At the training time, we align it with the monotonic alignment search, which gives a single hard target per token. But at inference, there is no MAS. We sample durations from a learned distribution with our STP. Sometimes these samples can be too short or too long. So basically, here you hear skips or repeats or stretched vowels. This gets words around multilingual or code switch boundaries with grapheme only inputs where token boundaries are ambiguous. Now, mispronunciation in Portuguese as well. So we feed letters instead of phonemes, right? So the model has to learn Portuguese's messy rules like nasal vowels, position dependent R, etc., etc. With only one Portuguese speaker in training, it overfits those patterns to its dialects and all of those. And then we also have the Portuguese gender gap. So Portuguese training lacked female voices, so the voice conversion to female Portuguese voices is weaker, and this is purely due to data coverage problems. So the first unstable durations is basically caused by the MAS, or basically having hard boundaries, that is we align completely fixed targets per token. So basically each token has assigned hard frames or hard speech frames that can cause problems. Also in mispronunciation Portuguese, it's basically overfitting to just one single Portuguese user, which could be solved by as adding phoneme support, or like something like grapheme plus phoneme mix with G2B fallback, and basically adding more Portuguese speakers. Same for the gender gap, we can have more female voice Portuguese speakers to fix this. For future work, we'll simply, as we said, basically we can stabilize duration predictor with the guardrails that I mentioned, add phoneme and mixed inputs to reduce mispronunciations, and also we can expand language and speaker diversity, and also use our TTS model to synthesize data source for low resource ASR training. So basically timing, pronunciation and coverage, each has a concrete fix, and we are executing on them in our future work. So now what we are suggesting is our extension, that is a GMM alignment, or basically Gaussian mixture models. So why we need it? As I said, the monotonic alignment search gives one hard alignment path per token. It is stable, but it cannot represent uncertainty. In real speech, the same token can be validly short or long depending on the context. For example, we use acha as like, let's say just acha, or we can have it like in a question mark or like acha. So in code switch speech, the mapping is even more variable. So training the duration model on a single path makes it brittle, or basically, though it gives us stability, we cannot map the uncertainty. And when we do the inference, the HDP basically messes up, and when we sample, the timing can wobble and give us some skips or basically lagging. So what we are adding is we add a lightweight GMM head after a text encoder. So for each token, it predicts a mixture of Gaussian time frames. So basically it's like a mean with a certain spread. So it basically gives us a soft alignment instead of a hard alignment. How it trains, so we basically keep our MAS as teacher and add a KL divergence loss so the GMM stays close to MAS when MA is confident, but can spread a bit when alignment is naturally uncertain. We enforce monotonicity by building our mean as a cumulative positive steps and clamp the variance to avoid over smoothing. So this helps us because it basically has minimum compute overhead, fewer timing errors. So that instead of using some other methods, when we use this, it does not really have much more architectural changes. We just need to add it after text encoder. So basically just we are adding some flexibility and uncertainty modeling without giving up our monitoring alignment such that is giving us stability.
Okay, so here is what we are trying to implement. We know that your TTS model works good with a single language in a sentence, but when we are trying to implement more than one language in a single sentence, that means code switch data, your TTS does not work that great. So we are trying to use GMM attention module with your TTS's MAS alignment so that it can work with code switch datasets also. Your code switch datasets also. First, we'll use GMM attention module. Instead of forcing a rigid hard alignment, we'll create soft probabilistic map for each audio frame. This will allow us to handle the uncertainty of code switching without failing. Then we'll train it jointly with our original MAS aligner. Using the MAS aligner as a teacher, we'll use two key loss functions. First, KL divergence to guide the learning, and another will be auxiliary loss function to reward the model for making confident alignments. To prove it works, we'll test our model on a Hindi-English dataset against the baseline. We'll measure for fewer skips and repeats, and also we are gonna get MOS score and similarity MOS score from human listeners to ensure it sounds natural. Ultimately, the expected outcome is a TSS model that is significantly more robust for code switched languages. Our solution is built on three key mathematical principles for a more robust alignment. First is Gaussian mixture models. We'll use a Gaussian mixture model to output a soft probabilistic alignment for each text token, capturing its position mu, which will be the center or mean, and uncertainty sigma, which will be the variance, given as the formula where pi, mu, and sigma's value will be calculated as parameter from our GMM attention layer. Second is KL divergence. We use KL divergence as a loss function to regularize our GMM, guiding it to learn from the stable alignment of the baseline MAS model. The formula is given where P will be the GMM alignment and Q will be the baseline MAS model's alignment. Third, we will use GMM attention. Our core innovation is a novel GMM attention mechanism where the output is the reach probabilistic structure of a GMM, making alignment more robust and interpretable. For this, we'll be using tools and libraries like PyTorch, NumPy, and Librosa, Matplotlib, and Seapon.
That's all from our side. Thank you for listening. We are Team Context Bandits, and these are the members of our team.